Have you ever wondered how analysts turn piles of data into clear, actionable insights? How businesses know what strategies work? How researchers test their ideas? Or how forecasters predict what might happen next? Behind all of these decisions lies one powerful toolkit: applied statistics. Statistics is not just about numbers or formulas. It is about using data to understand world, to summarize what is happening, to make informed guesses about what might be true, and to predict what could happen in future. Applied statistics takes these ideas beyond theory, helping us put them into action. It is bridge between mathematical concepts and real-world analysis, where insights begin to take shape. Welcome back to Shital's Data Desk, your one-stop destination for turning complex data concepts into clear, real-world insights. In today's video, we are taking next step on our data journey, applied statistics for data analysis, turning theory into insight. In this video, we will cover how descriptive statistics help summarize and explain data, how inferential statistics let us make predictions and test ideas, statistical tools to connect variables and support decision making, how to apply these tools in real world business example, and some common mistakes to avoid when interpreting results. By the end of this video, you will not only understand core methods of applied statistics, you will see how to actually use them to extract meaning, support evidence-based conclusions, and make smarter decisions. So, let's begin. What exactly is applied statistics? In simple terms, applied statistics is practical side of statistics. It is where theory meets reality. It is about using statistical ideas and tools to solve real world problems in business, healthcare, education, research, government, and beyond. Think of statistics as a journey. It starts with data, numbers collected from world around us. Then we use descriptive statistics to summarize and understand that data, finding patterns, averages, and variations. Next, we use inferential statistics to go one step further, making predictions or testing ideas based on samples rather than measuring everything. And finally, we use models like regression to uncover relationships and make informed predictions. In other words, applied statistics is the art of turning data into decisions. For example, imagine you work for an online retail company. You notice that sales fluctuate throughout the year, but you are not sure why. With applied statistics, you can use descriptive stats to summarize sales by month and spot trends. Use inferential methods to test whether seasonal changes really impact revenue. And use regression to predict next month's sales based on ad spend, weather, or holidays. Same approach applies in almost any field. In healthcare, you might analyze how different treatments affect recovery rates. In education, you might study how study time impacts exam scores. In finance, you might forecast stock returns based on past performance. Each time, core idea is same. We collect data, analyze it, draw conclusions, and make better choices. That's applied statistics. It helps us move from data collection to data understanding to data driven action. And just like any good story, it unfolds in chapters. First chapter is all about understanding your data, describing what's really going on before jumping to conclusions. Let's start there with descriptive statistics. Before we can analyze relationships or make predictions, we first need to understand data we already have. And that's where descriptive statistics comes in. First and most essential step in applied statistics. Descriptive statistics help us summarize and simplify large amounts of data so we can quickly see what is typical, how spread out data is, and what patterns might exist. Imagine you are looking at sales data from 1000 customer orders. Reading every number will not tell you much, but if you calculate just few summary measures like average order value, most common products, or how widely purchase amount vary, suddenly data starts speaking to you. Let's break this into three big ideas: center, spread, and shape. First, center. What is typical? Center tells us where most of our data tend to cluster. Three most common measures are mean, median, and mode. Mean or average is calculated as summation of x divided by n. Add up all values and divide by how many you have. Median is middle value when all data points are arranged in order. It divides your data set into two equal halves. And mode is simply most frequent value, one that appears most often. For example, If we look at week of coffee shop sales, on first 6 days it was 240, 260, 270, 280, 270, 300, and last busy day with 450. Now mean will rise because of this one large value, while median stays closer to what it typically on normal day. That is why it is always important to check both. Mean can be pulled by outliers, while median is more stable. Second, spread. How much does it vary? Now that we know what is typical, we also need to know how consistent or variable data is. Simplest measure is range, calculated as maximum minus minimum. It shows how far your largest and smallest values are. But to understand variation more precisely, we use variance and standard deviation. Variance measures how far each value is from mean on average, and standard deviation is simply square root of variance. Small standard deviation means data points are close to the mean, that is consistent. A large one means they are more spread out, that is variable. Third, shape. What does distribution look like? Finally, descriptive statistics also tell us about shape of our data. If data is evenly spread around mean, we call it normal distribution, a bell curve. If it stretches more to right, it is right skewed, common in income data, where few high values pull tail. If it stretches to left, it is left skewed. Visualizing data using histograms or box plots help you see these shapes instantly, making it easier to spot outliers and unusual patterns. In real analysis, you will rarely calculate all this by hand. Tools like Excel, Google Sheets, or Python's Pandas library make it simple. In Excel, you can use built-in functions like equals to average, equals to median, or equals to standard deviation. In Python, just one command, df.describe, gives you count, mean, standard deviation, minimum, maximum, and quartiles all at once. What matters is not formula itself. It is understanding what each number tells you about your data. So, before building models or testing hypotheses, always start with these descriptive summaries. Because if you don't understand your data, you can't trust any conclusions you draw from it. Now that we have summarized what is in front of us, let's move to next step, using data to infer patterns and test ideas. Inferential statistics, making predictions from data. If descriptive statistics help us summarize what we already know, inferential statistics help us go beyond what we know, using sample data to make conclusions about larger populations. Let's start with question. Why do we need inference at all? In real world, we rarely have data for everyone or everything. Instead, we work with samples, small manageable subsets of population. For example, company cannot survey every single customer, so it collects feedback from few hundred people. Hospital cannot test every citizen, so it studies sample of patients. Government cannot measure every household, so it runs census on subset. Here challenge is how do we make sure our sample truly represent population and how confident can we be in our conclusions? That's exactly where inferential statistics comes in. Two main goals of inferential statistics are first, estimation, using sample data to estimate population parameters, and second, hypothesis testing, checking if claim or difference is statistically significant. Let's unpack both, starting with estimation. Estimation shows how close is our guess. Suppose we survey 200 customers and find that their average satisfaction score is 8.2 out of 10. We can use that sample mean to estimate true population mean. But we also know there's uncertainty. Different samples might give slightly different results. So instead of giving single number, we give range called confidence interval. It start with sample mean, then add and subtract margin of error. For example, if our average satisfaction is 8.2 and our 95% confidence interval is plus minus 0.3, we can say we are 95% confident that true average lies between 7.9 and 8.5. This tells decision makers not just estimate but also how reliable it is. Second, hypothesis testing shows is difference real. Now, sometimes we want to test ideas or claims. For instance, is our new ad campaign increasing sales? Does new medicine work better than old one? Are two teaching methods producing different results? In such cases, we set up null hypothesis H null, assumption that there is no real effect or difference, and alternative hypothesis H1, which represents new claim we want to test. We collect sample data and calculate test statistics such as t-value or z-score. Then we compare this to threshold called critical value or find p-value which tells us how likely a result is if null hypothesis were true. If p-value is small, typically below 0.05, we say result is statistically significant and we reject null hypothesis. It means what we observe is unlikely to be random. There is likely real effect. Let's bring it to life. Suppose we want to know if new training program improves employee performance. We collect data from two groups, one before training, one after. Average score increased from 75 to 82. We run hypothesis test and get p-value of 0.02. That means there is only 2% chance this difference happened by random variation. So we can say with 98% confidence training program really made an impact. In tools like Python or Excel, hypothesis testing is easy to run. But what matters most is not just getting result, it is interpreting it correctly. Remember, descriptive statistics summarize what your data says. Inferential statistics help you generalize and test ideas. And together they form backbone of data-driven decision making. With that foundation in place, let's decode key statistical tools analysts rely on to turn theory into actionable insights. In applied analytics, one size never fits all. Choosing right statistical tool depends on your data type, your research question, and story you are trying to uncover. Let's simplify this. Whether you are analyzing data in Excel, Python, R, or Power BI, there are five foundational statistical tools every analyst relies on. First, descriptive summaries. These are your first look at the data. Mean, median, mode, quartiles, and measures of spread. They tell you what happened and help you spot trends or outliers at a glance. Second, probability distribution. Building blocks of inference. From normal to binomial to Poisson, distributions describe how your data behaves and help estimate likelihood of different outcomes. Third, sampling and confidence interval. Because analyzing an entire population is rarely practical, we work with samples, smaller, manageable slices of data. Confidence intervals then help us estimate what's true for population. With margin of uncertainty, we can measure. Fourth, hypothesis test. When you want to compare or validate, this is where you go. Comparing groups, use t-test or ANOVA. Comparing proportions, try chi-square test. These tools let us check if observed differences are real or just due to chance. Fifth, regression models. Now we move beyond description into prediction. Regression helps identify relationships and forecast outcomes. From linear regression to multiple and logistic models, these are the engines of modern analytics, predicting everything from sales growth to disease risk. Applied statistics is not about memorizing formulas. It is about matching right question to right approach. Each of these tools answer different kind of questions. What happened? Descriptive summaries. Why did it happen? Hypothesis test. What might happen next? Regression and prediction models. That is the real art of applied statistics. Not just running tests, but choosing wisely. So every analysis leads to meaningful actionable insight. Now that we have covered both descriptive and inferential statistics, let's see how these tools actually come alive in real world. Because at the end of the day, statistics is not just about numbers. It is about solving real problems, improving decisions, and turning data into meaningful actions. Let's start with business analytics. Imagine you work for an e-commerce company. Every day you collect thousands of data points, customer visits, ad clicks, sales, delivery times, and ratings. You use descriptive statistics to summarize what's happening. Average order value is 1200 rupees. Conversion rate is 3.5%. Customer satisfaction averages 8.1 out of 10. But that is only half the story. What if you want to predict whether customer will buy again or test if new ad campaign performs better? That is where inferential statistics comes in. You might run A/B test showing ad A to one group and ad B to another and use t-test to see if difference in sales is statistically significant. If your p-value is less than 0.05, you can confidently say new ad is performing better not just by chance. These insights help businesses make smarter data-driven marketing decisions. By now, we have seen how statistics help summarize, test, and predict. But even with base tools, it is easy to make mistakes that lead to wrong conclusions. So, before we wrap up, let's go over some common mistakes analysts make and how we can avoid them. Mistake 1. Confusing correlation with causation. Just because two things move together doesn't mean one causes other. For example, number of people who buy ice cream and number of sunburn cases both go up in summer. But ice cream doesn't cause sunburns. Real cause is third factor temperature. Best practice, always ask, could there be another variable influencing both? Use experiments or time based studies to verify causal links. Mistake 2. Ignoring shape of data. Many people apply formulas mechanically, assuming relationship is linear or data is normally distributed, when in reality it is not. If your scatter plot looks curved, mean and correlation may not tell full story. Or if your data has extreme outliers, average can be misleading. Best practice, always visualize your data first. Look for patterns, outliers, and shape before jumping into conclusions. Mistake 3. Over reliance on small samples. Small data sets can give unstable or misleading results. Few extreme values can shift your mean, inflate your standard deviation, or even reverse your correlation. Best practice, whenever possible, use larger representative samples. And when you can't, report confidence interval to show uncertainty in your estimates. Mistake 4. Misinterpreting p-values. P-value less than 0.05 doesn't prove something is true. It only means observed result would be rare if null hypothesis were true. Best practice, treat statistical significance as a signal, not a verdict. Combine it with effect size, context, and domain knowledge before drawing conclusions. Mistake 5. Cherry picking or p hacking. Sometimes analysts run dozens of tests and only report the ones that show strong results. That inflates false positive, making noise looks like discovery. Best practice, plan your analysis before collecting data. Use transparent methods and always report all your tests, even ones that didn't show significance. Mistake 6. Forgetting story behind statistics. Numbers alone don't make decisions, people do. Technically correct analysis is useless if it doesn't answer real question. Best practice, always tie your results back to business or research goal. Ask, what does this number mean in context? What action does it suggest? In short, good statistics is not just about doing math correctly, it is about thinking critically. Best analysts don't just crunch numbers, they question assumption, check data quality, and interpret results with care. Because in real world data analysis, precision matters, but judgment matters even more. Before we wrap up, here is quick recap. Applied statistics helps us turn raw data into clear decisions. Descriptive statistics summarizes what is happening, while inferential statistics help us test ideas and make predictions. Together they form core of real-world data analysis towards mastering data literacy. You now understand how to think statistically, interpret results, and see data as more than just digits on screen. But we are not stopping here. In our next video, we will go deeper into action, learning descriptive statistics in detail, from summaries to visual stories. Because theories give you understanding, but practice gives you mastery. And as always, if you found this video helpful, make sure to like, share, and subscribe. And let's continue turning numbers into knowledge and knowledge into impact.